Hi guys, chapter 11 today, going over somatic and autonomic motor systems, meaning our nervous system has two motor divisions. One is under voluntary control, we call that somatic motor division, and one under involuntary control called autonomic motor divisions. So we're going to go over comparing and contrasting the two motor divisions, um, emphasizing the autonomic motor system. So when you learn from anatomy, um, most likely the autonomic motor system, you learn that under another name. It's called the ANS. ANS stands for autonomic nervous system. That ANS, autonomic nervous system, it is the autonomic motor system. You can say autonomic, or you can say visceral. VISCERAL, visceral motor system. Now, there's a typo in your schedule. It says that this chapter 11 is over 2 recordings, and chapter 12 is over 1 recording. It's the opposite. Chapter 11, which is this recording, will last within 1 single recording, and the next recording, chapter 12, will require 2 recording sessions. FYI. Okay, now, so we're going to go over somatic motor pathways, autonomic nervous system, and then specific signaling mechanisms for the autonomic nervous system, specifically going over the receptors and going over the type of neurotransmitters. So bringing to another level what we've learned. Actually, there's nothing new, it's just applying what we've learned from the previous unit about excitable tissue. So we are still part of the nervous system, but we are going over the motor division, more specifically emphasizing the autonomic / visceral motor division of the nervous system. So that's the gist for the lecture. So with that said, let's get this thing started with the first slide. So when we say somatic nervous system, we are talking about somatic motor pathway. We are talking about voluntary control of our skeletal muscles, right? So when we say effector organ for somatic, we are talking about skeletal muscle, right? Skeletal muscle here means organ, okay? One skeletal muscle is one organ. One skeletal muscle fiber is one cell. That you should know it by now. That's anatomy, knowledge, right? So again, when we say skeletal muscle fiber, we are talking about the cellular level. We're talking about one cell. Okay, so skeletal muscle fiber, it means the same thing as skeletal muscle cell. But when we say skeletal muscle, we're talking about an organ. We're not talking about a cell. So when we say effector organ, we're talking about the skeletal muscle. So there's only one type of target organ or one type of target effector organ, and that's skeletal muscle for the somatic motor pathways. So we are dealing with two neurons, upper motor neuron and lower motor neuron. The cell body or the soma of the upper motor neuron, right? Soma, S-O-M-A, cell body of that upper motor neuron resides in the primary motor cortex, right? So the cell body of the upper motor neuron is physically located in the primary motor cortex. In anatomy, this primary motor cortex, most likely you learn that as precentral gyrus. That's its anatomical name. The precentral gyrus, that's its structural name, and its functional name, it's called primary motor cortex. It is part of the cerebral cortex. It belongs to the frontal lobe, okay? And that upper motor neuron sends axons down to synapse with the lower motor neuron. And for the lower motor neuron, the soma or the cell body of the lower motor neuron is here. And it's not random. It is specifically in this area here. And that area is called the anterior gray horn of the spinal cord, okay? A for anterior or ventral, but I prefer you learn as anterior because we are walking on two limbs. We're not a four-limb, animal. So for a dog would be ventral, but for humans would be anterior gray horn. And the anterior gray horn is a region, specific anatomical region within the spinal cord. And that region contains all the cell body of lower motor neurons. Again, one more time. The anterior gray horn, there are two of them. There's a right anterior gray horn and there's a left anterior gray horn, right? Each anterior gray horn houses hundreds, thousands of cell bodies, and the cell bodies belong to the lower motor neuron. And the lower motor neuron will send its axon out, leaving the spinal cord, and they're gonna innervate the effector target, the effector cell, in this case, skeletal muscle fiber, right? So again, one more time, when we say skeletal muscle, we are talking about the entire organ. And when we say skeletal, this fiber here, We're talking about the skeletal muscle cell. Okay. Now, why do we call skeletal muscle cell fiber? The reason is because the shape of the cell. It's a long cell, looks like a cylinder, looks like a fiber. So we call it skeletal muscle fiber. Same thing with cardiac muscle. You can say cardiac muscle cell or cardiac muscle fiber. The only type of muscle that is not called a fiber is a smooth muscle. You don't call them skeletal, you don't call them smooth muscle fiber, you call them smooth muscle cell, okay? So you say smooth muscle cell, cardiac muscle fiber / cardiac muscle cell, skeletal muscle fiber / skeletal muscle cell. So the upper motor neuron, the cell body resides within the primary motor cortex, sends axons down all the way to either the brainstem or the spinal cord. If it's in the spinal cord, it's located, the synapse is located within the anterior gray horn. So that synapse, it synapses the axon terminal from the upper motor neuron synapses with the cell body of the lower motor neuron. And the cell body of lower motor neuron sends axon out through the nerves, spinal nerves, to get to the effector organs, in this case, skeletal muscle fibers. Now, axons, when we talk upper motor neurons, axons of upper motor neurons, they are called tracts. Right? Specifically, fiber tracts. Whereas this here, that's an axon of lower motor neuron. Yeah. And they are bundled into this structure here, and we call that a nerve. So axons do not travel by themselves. Axons are bundled. Axons are aggregated. And if these axons run within the brain or the spinal cord, we call them fiber tracts. And if the axons physically run outside of the brain and outside of the spinal cord, we call them nerve. Specifically cranial nerves or spinal nerves, right? That's from anatomy. So you should know that, okay? Now, what is interesting, again, this is anatomy. These tracts, upper motor neurons, they have names, different names as they run through the central nervous system. They have different names. This tract here, it starts out as the internal capsule. That's from anatomy. So you have bundles of axons belonging to the upper motor neurons. As they run through the cerebrum, they are called internal capsule, right? And as the same axons leaving the cerebrum and moved, for example, down to the brainstem, then they change the name. And they change the name to cerebral peduncle. Cerebral, Cerebral, peduncle, Peduncle. This cerebral peduncle do not mix up with the cerebellar peduncles. That's different, right? This cerebral peduncle is an aggregation bundles of axons belonging to the upper motor neurons. And these axons are running through specifically the first part of the brainstem, which is the midbrain. So when they run through the midbrain, you call them cerebral peduncle. And they run down to the medulla. When they are in the medulla, starting in the medulla, they change their names again. And they are called differently, the pyramids. And as they leave the pyramids and they go into the spinal cord, they change the name again. They change to cortical spinal spinal tract. Now the corticospinal tract, if you pay attention to the word, let's break the word down. The first part is cortical. The first part is where it begins, the pathway. So this is the start of the pathway. And the word spinal, this is where the pathway ends. So if you start and cortical, that's because of the cortex. So this is the cerebral cortex, the most intelligent part of the brain. Right, more specifically, the primary motor cortex. That's where the word cortical comes from. And spine ends in the spinal cord. So if you have a pathway that begins at the brain and ends at the spinal cord, you know that this is a motor pathway. Right, so this is the trick. So corticospinal, if you have a blank during a test, think about it. Break the word down. Cortical, it begins, it starts in the brain. Spinal, it ends in the spinal cord. So information starts in the brain, it ends in the spinal cord. It can only be motor. It cannot be sensory. Sensory means it begins in the spinal cord and will end at the brain, right? In this case, it's the opposite. So cortical spinal tract, that's a motor pathway. More importantly, it's a somatic motor pathway because the target, it's a skeletal muscle, allowing you to voluntarily, to consciously control these muscles, right? You can decide at will to write slowly, to write quickly, to run slowly, to run really fast. So on a voluntary basis. And that's part of the somatic nervous system, somatic motor pathway. Motor unit, very similar to a sensory unit. A sensory unit is one single sensory neuron serving a defined number of receptors, sensory receptors, connecting to that sensory neuron. Motor unit is the same thing, one single motor neuron innervating a specific number of effector cells, right? In this case, skeletal muscle fibers. So motor unit is one lower motor neuron innervated an defined number of skeletal muscle fibers. SKM stands for skeletal muscle fibers. Okay. So you can have small motor units, large motor unit. In humans, the small motor unit is innervating anywhere from between 2 to 3 skeletal muscle fibers. So small motor unit innervating 2 to 3 skeletal muscle fibers. Skeletal muscle cells. And the functionality of that is these motor unit generate exquisitely accurate movements, right? So this is precision guided movement. Let's say you do a surgical procedure using small motor units. You play a classical concerto piano, you use small motor units. So if you are using your fingers and you have these tasks that requires high accuracy, precision guided movements, uh, then you use small motor units. The advantage, exquisitely accurate. The disadvantage, they are weak because they innervate only 2 to 3 skeletal muscle cells, so they cannot generate a lot of tension, right? So the smallest motor unit is 2 to 3 skeletal muscle cells, skeletal muscle fibers. In humans, we do not have motor unit as small as one lower motor neuron innervating one skeletal muscle fiber. We do not have that type of connection. We do not have that type of innervation pattern. The smallest we have is 2 or 3 skeletal muscle fibers innervated by the same lower motor neuron. And the other extreme, so from 2 to 3, it can go all the way to 4,000 skeletal muscle fibers. So that's the large motor unit. The large motor unit is one single lower motor neuron innervating up to 4,000 skeletal muscle fibers. Okay. The functionality of it, they generate outstanding, tremendous amount of power. So they can generate a lot of tension, like kicking a football 60 yards downfield, right? Punching someone. So because of they can recruit, they can cause a contraction up to 4,000 skeletal muscle fibers. So they can generate a lot of tension, a lot of force. That's the advantage. The disadvantage is they do not have, they cannot generate accurate movements. They are not precision guided movements. They are power guided, power generated movements, right? So for every single muscle as an organ, you have a mixture of different sizes in terms of motor units. And that ratio between different sizes of motor units within each of your skeletal muscle is dictated by your genes. This is dictated by genetics, right? You cannot trick nature. So, for example, some people have a bulky physique. They would be, great, for example, generating powerful sprint. They would be great sprint short distance runners. Other people have a slender physique, and they would be more adapted to long distance running because of the composition of these different types of muscles with different types of motor units. And that's dictated by genes. However, you can train, you can trick your body to change your muscle composition, but that training requires, it's intense training, and it can last, up to 3 years of training before you can change the ratio of these different motor units. But you can never, ever cheat nature, because as soon as you stop your training, the ratio reverts back to the genetic makeup that you are made of. So changing motor muscle appearance based on function, based on training, is only temporary. As soon as you stop the training, everything goes back to normal, right? Because just you cannot change your genes. And then also, what is unique about the skeletal muscle is they display a new concept called symmetrical innervation pattern, meaning they innervate the skeletal within the motor unit symmetrically. So let's say you have a motor unit, a neuron coming down, and you have all these muscles. Let's say we have 1, 2, 3, 4, 5, and 6, right? So this, it comes, it will innervate symmetrically, meaning it comes in here, it innervates this one, sprouts out here, it innervates this one, and it comes down here, it innervates that one. So that's one motor unit with 3 skeletal muscle fiber. So it is innervating this one, 1, 2, 3. So it's not innervating on one side only, right? So this is symmetrical. And that's important because it allows, when you contract, the entire muscle contract, and not only part of the muscle is contracting. And you're showing here the 3 motor neurons, 3 motor units with different colors. Each motor unit, each motor neuron is innervating a specified number of skeletal muscle. So this is one single skeletal muscle cell. This is another one. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 skeletal muscle fibers innervated by 3 different lower motor neurons. And this is important. One skeletal muscle fiber is innervated by only one lower motor neuron. This skeletal muscle fiber is innervated by lower motor neuron 1. Okay? This muscle fiber cannot be innervated by motor neuron 2, cannot be innervated by motor neuron 3. It is dedicated, reserved for motor neuron 1, period. So all the skeletal muscle fibers that are innervated by motor neuron 1 for the entire lifetime, they will be innervated by motor neuron 1. For example, this skeletal muscle fiber is innervated by motor neuron 2. So its entire lifetime, it is innervated by motor neuron 2, this one. Same thing with this one, same thing with this one, by motor neuron 2. And motor neuron 3 is this one, that's it, right? So the point is each skeletal muscle is exclusively innervated by the same lower motor neuron throughout the lifetime of that skeletal muscle fiber. We briefly talked about this. So when we say innervation, when a neuron, the lower motor neuron, comes in to interact with the skeletal muscle fiber, there's no physical contact between the two, right? So the yellow structure here, this is part of the lower motor neuron, the axon and the axon terminal of the lower motor neuron. Whereas this part is the skeletal muscle fiber, skeletal muscle cell. And there's a microscopic space here. So the two cells are not touching each other, right? So that separation exists. It's microscopic, but it exists. So there's no physical contact. And that space is called NMJ. And what is NMJ? NMJ stands for neuromuscular junction. So do not call this a synapse. We learned this, right? Synapse is applicable only between two neurons. The microscopic space between two neurons, we call it a synapse. But the microscopic space between a muscle cell and a neuron, we call it a junction. In this case, between the skeletal muscle cell fiber and a lower motor neuron, we call it neuromuscular junction. And this is also anatomy. We should know that. Okay, so you have the neurotransmitter in the axon terminal, ACH. That's the acetylcholine. as a neurotransmitter, a chemical messenger stored in the synaptic vesicle. The same concept applies. Axon potential arrives, propagated down the axon. They hit the axon terminal, which is called the terminal bouton here, but that's axon terminal. And they cannot be spread through the membrane of the axon terminal because the plasma membrane at the axon terminal does not have voltage sensitive sodium channels. Because of that, the action potential dies when it hits the axon terminal. But that depolarization signal spreads throughout the axon terminal. And there's another type of ion channels, voltage sensitive calcium channel, that opens and allows the massive influx of calcium, inducing the synaptic vesicle to fuse with the cell membrane of the axon terminal to release the neurotransmitter into the neuromuscular junction. And the neurotransmitter diffuses across the neuromuscular junction by simple diffusion. So here's the voltage sensitive ion channel. They get activated by the depolarization. They open, calcium flux in. Calcium induces the fusion of the cell membrane between the cell membrane and the membrane of the vesicles. When they fuse, this vesicle can empty the content into the neuromuscular junction. And that content are basically your neurotransmitter molecules, ACH, acetylcholine. And the acetylcholine binds to its own exclusive receptor. We call it nicotinic cholinergic receptor, which is an ion channel. And that ion channel opens, fluxes 3 ionic species, allows sodium to get in, so sodium influx, not shown here, but allows also calcium influx and potassium efflux. And there's a net gain of positive charge, and it will depolarize the membrane. And in the case of the skeletal muscle fiber, the cell membrane of that skeletal muscle fiber is called sarcolemma. Right? We don't call cell membrane a plasma membrane, we call it sarcolemma. So skeletal muscle cell membrane here, we call it sarcolemma. sarcolemma. Now, when the sarcolemma is depolarized by the nicotinic cholinergic receptor, it will generate a very, very powerful depolarization called EPP. Stands for end plate potential. End, E-N-D, plate, P-L-A-T-E, potential, right? This end plate potential is so huge, so large, it is always above threshold. This is another concept. At the neuron, it's not always above threshold. In fact, most of the time, it will not get to threshold. But when acetylcholine, ACH, binds to the nicotinic cholinergic receptor, that ion channel opens up. The massive accumulation of positive charge causes the membrane to depolarize. The amplitude of that depolarization signal is so great that it will always satisfy the threshold potential. So the sarcolemma here, there's a threshold potential that would be satisfied by the EPP. Once that happens, on the sarcolemma, you also have voltage sensitive sodium channels and voltage sensitive potassium channel there to give birth to an action potential on the sarcolemma. So in other words, this entire process is to recreate the action potential on the sarcolemma, on the cell membrane, on the plasma membrane of the skeletal muscle fiber. That's the entire idea. So the neuron, the lower motor neuron, has a signal, and that signal is spread now to the muscle. And once the action potential is being generated at the sarcolemma, it will spread throughout the muscle. So that's a signal notifying the muscle, hey, you need to contract. Now, once the acetylcholine is released into the neuromuscular junction, ACH, one thing that's unique about it, the nicotinic cholinergic receptor requires 2 ACH binding before it can open. There's one here, and there's another one here, right? So the nicotinic cholinergic receptor requires 2 ACH molecules binding for each ion channel. For each nicotinic cholinergic receptor, it takes 2 ACH molecule to bind before the channel can open. And once ACH has done this job, it opens a nicotinic cholinergic receptor to create the EPP, to create the end plate potential. That ACH needs to be neutralized. And that's done by an enzyme at the membrane, acetylcholine esterase. So this is a membrane-bound enzyme. It's written at uppercase A, uppercase H, lowercase, uppercase A, uppercase C, lowercase h, and uppercase E. That's the enzyme. ACHE, acetylcholine esterase. And it will cut acetylcholine into choline and acetic acid. And the neuron picks choline up to recycle to make more acetylcholine neurotransmitter, right? So acetylcholine, it's cut, hydrolyzed into choline and acetic acid. And choline is picked up, recycled by the axon terminal of that lower motor neuron. And that lower motor neuron will make more ACH. So each skeletal muscle fiber requires innervation from a lower motor neuron. And this requirement is for life. And this is important. If the lower motor neuron stops communicating with the muscle cell, the skeletal muscle cell will shrink, will die, will atrophy, and will die. This is what happens to individuals who have sustained spinal cord injuries, paraplegics, right? And that's why their lower limbs are so small, so shrunk down, is because of that. So the skeletal muscle, as soon as they stop receiving innervation from the lower motor neurons, they stop reacting. They basically, it's not healthy for them. So they atrophy and ultimately they die. So that's one of the caveats for skeletal muscle tissue is, yes, you can control them on a voluntary basis, but they require innovation. They require neural input 24/7, even when you're sleeping. The only time when you are paralyzed is when you are during your sleep, and only when you're actively dreaming, right? During your REM stage in your sleep, rapid eye movement. This is to prevent you from acting out in your dreams. Let's say you're dreaming, you're hitting someone. If that's not doing its job, then you will hit your wife or you will hit your husband during your sleep. So when you're actively dreaming, REM sleep phase, your muscles are paralyzed on purpose. Outside of that, they constantly receive innovation. there's always a baseline muscle tone maintaining the health of your skeletal muscle. Even if you're sitting, even if you're standing, there's always a muscle tone there to basically making your skeletal muscle contract at the basal level. As soon as that innervation goes out, the skeletal muscle fiber dies. Whereas the other two types of muscle, the cardiac muscle, which we're going to learn in the next unit, and the smooth muscle, during the fourth unit, they don't need neural innervation. They don't need neural control. Right? Even though you cannot control them on the voluntary basis, they are independent. They can work on their own. So that's the advantage of smooth muscle and cardiac muscle. They don't require 24/7 neural input. However, the downside, you cannot control them on a voluntary basis. Now, the autonomic nervous system has three divisions, not two. There's the sympathetic division, the parasympathetic division, and the third one is the enteric division, which we're going to talk about when we talk about the digestive system. So the enteric nervous system is also part of the autonomic nervous system. So sympathetic, parasympathetic, and enteric, right? So 1, 2, 3. Most medical textbooks will say 2, but they ignore that enteric because they classify enteric under the digestive system. But when we talk about visceral motor division, autonomic motor division, autonomic nervous system, it truly consists of 3 divisions: sympathetic division, parasympathetic division, and enteric nervous system. So we're going to focus on sympathetic and parasympathetic for the remaining of today's recording. And then we're going to revisit enteric nervous system when we talk about the digestive system. Now, the sympathetic and parasympathetic division have diametrical function. They oppose one another. They have opposite functions. So oftentimes they are not working together. Most of the time they don't. When the sympathetic is activated, the parasympathetic is attenuated and vice versa. And I think I've mentioned this before. The only time when both sympathetic and parasympathetic come as a team, work together, this is during sex. And not only during sex, it's only when the individual is close and climaxing. That's exactly when these two autonomic divisions come together to work as a team. Outside of that, they don't work together. The sympathetic is activated under emergency situation. It's also known as a fight or flight situations, whereas the parasympathetic is under rest and digest situations. So when, for example, you're running late for class, that's sympathetic. When you're being embarrassed, sympathetic. When you're writing an exam, sympathetic. But when you're eating, that's parasympathetic. After the meal, you take a cigar, you relax, parasympathetic. You're enjoying nature with, right after the meal with a cigarette, a cigar, and you're enjoying life with a drink with your wife, your loved one, that's parasympathetic, right? Now, most visceral organs receive both innervation from both division. And we call that concept dual innervation. As you can see here, the lungs, our lungs receive both sympathetic and parasympathetic innervation, right? So effector organs, so most visceral effector organs receive sympathetic innervation and parasympathetic innervation. We call that dual innervation. However, there's a list of organs or structures that receive only sympathetic division. And that's the exception to the dual innervation statement, right? Receiving only the sympathetic division. And they are smooth muscle, from the walls of blood vessels. BVS stands for blood vessels. For example, arterioles, right? So the smooth muscle lining the walls of blood vessels receives only sympathetic division. The smooth muscle that are basically wrapping around your hair follicles, the arrector pili muscle, also receives only the sympathetic division. This muscle, when it contracts, it gives you goosebumps. Arrector pili, ARRECTOR. That's an R, that's not a V. TOR and pili, PILI. You also have adipocytes. They're only innervated by the sympathetic division. Adipocyte means cells of adipose tissue, fat cells. ADIPOCYTES. Right? So those are the three main effector targets exclusively served by sympathetic division. They do not have parasympathetic innervation. The last one I'm going to add in red because it's a special case. The heart. The cardiac muscle of the heart receives both sympathetic and parasympathetic. But the heart, the conduction system of the heart, only receives sympathetic. Conduction or conducting system, C-O-N-C-U-C, no, sorry, conduction, C-O-N-D-U-C-T-I-O-N. The conduction system of the heart, this is where the it gives rise to the rhythm of the heart, right? So for example, the pacemaker system, the SA node, the AV node, the Purkinje fibers and all that you learn from anatomy. So that's part of a conduction system. They are bona fide cardiac muscle cells, cardiac muscle fiber. However, they have lost the ability to contract, but they have gained the ability to generate spontaneous action potentials. They dictate how fast and how slow your heart beats. They control, they regulate, they dictate the rhythm of your heart. And together, all these cells, they're called the conduction system. And that conduction system is under the innervation of only sympathetic division, not parasympathetic. So the sympathetic can increase the rate of your heart. The parasympathetic is not involved. The sympathetic and parasympathetic can control the strength of contraction of your heart. That's different, right? So the mechanical component of the heart is under both dual innervation. The mechanical component is under the influence of sympathetic and parasympathetic. But the electrical component of the heart, the conduction component of the heart, is only under sympathetic division. There's another one I want you to add because I'm running out of space here. The adrenal gland, which is above the kidney. This structure here. The adrenal gland is specifically under sympathetic innervation. So that brings to 5 targets for you to learn. So I want you to know those 5 effector targets under exclusively by innervated by sympathetic division. So ANS, involuntary nervous system, introducing, or shall we say review, because I expect you to know this. Ganglia, 1 ganglion, 2 or more ganglia, right? So this is 2 or more, this is plural. And the definition of a ganglion is basically an aggregation of bundles of cell bodies of neurons. But that's just half of the definition. Bundles of cell bodies of neurons. But these cell bodies are physically located outside of the spinal cord, outside of the brain. We call it a ganglion. Because if we have bundles of cell bodies and the cell bodies are located within the brain or within the spinal cord, then we call that a nucleus. It has nothing to do with the nucleus of a cell, right? So nuclei for plural. Again, nuclei are a bundle of cell bodies, but the cell bodies are located within the central nervous system. So part of within the brain or the spinal cord. Whereas ganglia means the bundle of cell bodies are located outside of the brain and outside of the spinal cord. Okay? So when we say motor ganglia, it is only autonomic. We do not have somatic motor ganglia. And we have, so no somatic motor ganglia. We do have somatic sensory ganglia, right? Somatic sensory ganglia means the cell bodies of the first order neuron that are located in the dorsal root ganglia. So the dorsal root ganglia are in fact somatic sensory ganglia. But we do not have somatic motor ganglia. We have autonomic or visceral motor ganglia. That we do have. We're going to talk about here. So this is autonomic ganglion. You can, instead of saying autonomic, you can say also visceral ganglion. And when we talk about somatic motor pathways, there's only one target organ, right? One type of effector organs. But when we talk about ANS pathways, autonomic motor pathways or visceral motor pathways, the question is, what are the effector organs? And they're listed here. Cardiac muscle, smooth muscle, glands such as sweat glands, and adipose tissue. Oh, sweat glands, add on the previous slide, the structures that are exclusively innervated by sympathetic division, sweat glands. Sweat glands are also examples of structures that are exclusively innervated by the sympathetic division. The parasympathetic division does not innervate sweat glands. Okay. And we talk about adipose tissue. So those are specific target for the autonomic nervous system. And how do we distinguish between sympathetic and parasympathetic division? There are many ways, both structurally and functionally, which is the topic for the next few slides. And let's go over them to address this question here. So how do you distinguish between sympathetic and parasympathetic division of AD-ANS? You might want to write it down here by two ways. You can do it based on function or based on structure. So based on structural differences. Structural. structural, or based on functional differences. So based on structure and based on function. functional, functional, right? So you can use anatomical differences or physiological differences. Structural / anatomical, functional / physiological. And the first example is, let's begin with the sympathetic division. So for the sympathetic division, it has different names. So sympathetic division, that's a functional name. Anatomical name is thoracolumbar division. The reason is this division exits between T1 and L2. So the entire thoracic, all 12 thoracic vertebrae, and the first 2 lumbar vertebrae. That's what's called thoracolumbar, okay? Because it exits between T1 and L2, thoracolumbar. And that's from anatomy also, T1 to L2. I hope you remember that we have 12 thoracic vertebrae and 5 lumbar vertebrae. Okay, so from T1 to L2, that's your sympathetic division. That is exactly where the axons are exiting the spinal cord. And there are 3 types of ganglia under sympathetic division. with 3 different names, obviously. So the first type is called the sympathetic chain. The second type is called adrenomedullae. And the third type is called collateral ganglia. So those are your 3 types of sympathetic ganglia. So shown here, you have your sympathetic chain. There's one here, there's one here, and there's one here. So 3 ganglia that are part of a sympathetic chain. You have your adrenal medulla, which is the deeper region within the adrenal gland. That's the second type of ganglia, sympathetic ganglia. And you have your third, collateral ganglion. So for the adrenal medulla, you have 2, one in each adrenal gland, right? So the right adrenal medulla, the left adrenal medulla. The collateral ganglion, you have 3 of them. They are located anteriorly in front of your vertebral column, whereas the sympathetic chain is on the side of your vertebral column, right and left. So this, the right side is here, the left side this way. So the names of the 3 single collateral ganglia, we have the superior mesenteric ganglion, inferior mesenteric ganglion, and the celiac ganglion. So those are the 3 single collateral ganglia by name. Okay. Celiac ganglion, superior mesenteric ganglion, inferior mesenteric ganglion. Now, if you look closely, you have the preganglionic neuron, you have the postganglionic neuron. And this is your ganglion, right? Containing cell bodies of neurons that are physically located outside of the spinal cord. That's what we call it, a ganglion, right? The preganglion neuron, this axon here, is myelinated. We're going to learn that later. So this axon, this axon is myelinated. This axon is unmyelinated. And you learn that from anatomy as well. The white and gray communicons. So we're going to talk about that. The white one is because of the myelination. So they belong to bundles of axons from the preganglionic neuron. And the gray is from unmyelinated axons, bundles of axons belonging to the postganglionic neuron, right? And down here, the chromaffin cells, if you look closely, the chromaffin cells replace the postganglionic neuron. You have the preganglionic neuron here, but you don't have the postganglionic neuron. It's replaced by chromaffin cells. Because of this, the adrenal medulla, it's called a modified ganglion. Okay, modified ganglion. due to the fact that the postganglionic neurons have been replaced by another type of cells called chromaffin cells. So the chromaffin cells release chemical messengers not as a neurotransmitter, release chemical messengers as hormones because they are going into the bloodstream. Yeah. And down here, the collateral, we still have the preganglionic neuron, the postganglionic neuron. Only in the adrenal medulla, you do not have the postganglionic neuron. It's replaced by chromaffin cells. So I just talked about it, the white and gray ramus communicons. Rami, that's plural, one ramus, two or more rami. So white axons, preganglionic neurons, because these axons white because they are myelinated. They have myelin sheathing around them. Myelinated, M-Y-E-L-I-N-A-T-E-D, myelinated. Whereas the gray ramus, these axons are unmyelinated. They're not myelinated. Right. Unmyelinated, U-N-M-Y-E-L-I-N-A-T-E-D. Since myelin is white because it's lipid, fat-based, it looks white. That's why we call it white ramus. The axons are not myelinated. They look grayish, so we call it gray ramus. So the gray ramus are actually bundles of axons that are belonging to the postganglionic neurons. The white ramus are bundles of axons that belong to preganglionic neuron. And one more thing. Since the cell bodies of these neurons locate at different places, they're also classified differently. The preganglionic neurons are considered to be central neuron. They belong to the central nervous system because the cell body is located in the spinal cord, central neuron. And in the spinal cord, it's not random. They are located here. The cell bodies on the lateral gray horn. This is between T1 to L2. The thoracolumbar division, the sympathetic division, right? So the cell body of the preganglionic neurons are specifically located at the lateral gray horn on the side. Lateral, L-A-T-E-R-A-L, lateral gray horn. Whereas the cell body of the postganglionic neuron are located in the ganglion itself. So that's the cell body, right? And this is your ganglion. This is the entire ganglion. So each ganglion contains hundreds of cell bodies, and these cell bodies are called belonging to postganglionic neurons, and they send the unmyelinated axons out to serve the effector. So the effector here is cardiac muscle, smooth muscle, glands, adipose tissue. So why white? That's because of the myelin. Why gray is because lack of myelin sheathing around axons. So white is because of the myelinated axons and gray because unmyelinated axons. And that's anatomy too. There's nothing new here. So the adrenomedullae, like I mentioned earlier, 80% is epinephrine, 20% is norepinephrine. Same chemical having two names. Epinephrine is also known as adrenaline. So when epinephrine is released into the bloodstream, you go through what's called the adrenaline rush, right? This is when your body is preparing itself to face an emergency situation. This is a fight or flight situations here. So when your adrenal medulla, right and left adrenal medullae releases epinephrine and norepinephrine into the bloodstream, they are working as hormones. They're not working as neurotransmitter, because what is unique about them is the same chemical, they can function as neurotransmitter or hormone, depending on where they are released into. If epinephrine is released by, for example, the post-ganglionic neuron into a neuromuscular junction interacting with a cardiac muscle, then that epinephrine is functioning, acting as a neurotransmitter. But if this epinephrine is released by the chromaffin cells into the bloodstream, this epinephrine is not acting as a neurotransmitter. It is acting as a hormone. Okay, so that's a new concept. So the same chemical can function as a neurotransmitter or as a hormone, depending on where it is released into. If it is released into a synapse or a neuromuscular junction or neuroglandular junction, then it is acting as a neurotransmitter. But if it's released into the bloodstream, then it functions as a hormone. Now, epinephrine and norepinephrine, or adrenaline and noradrenaline, they fall under another name, catecholamines. catecholamines. And catecholamines have three examples. It has adrenaline, it has noradrenaline, NA. So A stands for adrenaline, NA for noradrenaline, and the third one is dopamine. Dopamine is mainly released into the brain, within the brain. DOPAMINE, dopamine. So those are three examples of catecholamines, three specific examples of catecholamines called adrenaline, noradrenaline, and dopamine. Adrenaline is also known as epinephrine, and noradrenaline is also known as norepinephrine. Moving on to parasympathetic division. Here, they exit the central nervous system at different places. That's what's called craniosacral. Cranial, they exit throughout of the brainstem, through the cranial nerves and sacral through the pelvic, sacral spinal cord through the pelvic nerve. And what you're looking at here is, look at the axon, right? This is the preganglionic neurons. The axons of the preganglionic neurons are very long compared to the axons of the preganglionic neurons in the sympathetic division, because the sympathetic division, the ganglia are closer to the spinal cord. So axons of preganglionic neurons are longer in the parasympathetic compared to the sympathetic. That would be an anatomical structural differences. Same thing here. Axons of postganglionic neurons are shorter from the parasympathetic compared to the sympathetic, because axons of postganglionic neurons from the sympathetic are much longer than the ones compared to the parasympathetic. Okay, if you go back to the previous picture, you'll see it. So that's structural differences. So the first structural difference is where they exit the central nervous system. So sympathetic exits between T1 and L2, whereas parasympathetic is from the brainstem and the sacral spinal cord. That was the first structural difference, where they exit the central nervous system. The second structural difference is the length of the axons, specifically the length of axons from preganglionic neurons and the length of axons from postganglionic neurons. And the third difference is the ganglia themselves. Sympathetic has 3 types of ganglia. Parasympathetic has only 2 types of ganglia. So that was the third difference. The fourth difference is the ganglia in the sympathetic are closer, especially the chain ganglia are closer to the spinal cord. In the parasympathetic, the ganglia are closer to the target organ. Okay, so those are anatomical structural differences between sympathetic and parasympathetic division. So you can see here, and then here is mainly functional differences. So you see here, this is the axon of the preganglionic neurons, short axon. All 3 are based, so this is the short here, but parasympathetic is long axon, okay? So when I said length of the axon, that's what I meant. Coming back here. So you have your chain ganglia, you have your adrenal, modified ganglion, and you have your collateral ganglion. So this is the functionality here. The neurotransmitter is ACH, ACH, ACH. So the preganglionic neuron, they all release ACH, 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 ACH. And when a neuron releases ACH, you call it cholinergic, cholinergic, cholinergic. So when you release the chemical messenger called acetylcholine, ACH, it's cholinergic. This is sympathetic division. So let's erase that. Now the same thing for the postganglionic neuron. Postganglionic neuron, And here we don't have a postganglion neuron. We have the modified ganglia chromaffin cells. Okay. It releases another type of chemical messenger, norepinephrine, epinephrine, norepinephrine. And for that, it's called adrenergic. Adrenergic. And okay, so adrenergic for NE, NE, and epinephrine is also adrenergic. ACH is cholinergic. Okay, so that's for the neurotransmitter. Now for the receptor. The receptor is nicotinic cholinergic receptor. Nicotinic cholinergic receptor. Nicotinic cholinergic receptor. All of those receptors are for ACH. And this type of receptor, nicotinic cholinergic receptor, is an ion channel. It's an ionotropic receptor. It's a fast response receptor. Okay, so that's for the ACH receptor. Now for the epinephrine and norepinephrine receptor, we have adrenergic receptor, adrenergic receptor, adrenergic receptor. And these receptors are not ion channel. These are G protein coupled receptor. These are metabotropic receptor. These are slow response receptor. They are not ion channels. And on that, I will ask you to learn on a table, because there's nothing cerebral here. Table 11.1, page 311. And there are different adrenergic receptor. There are two families. There's the alpha adrenergic receptor and there's a beta adrenergic receptor. For alpha, there's alpha 1 and alpha 2. And they are important because we come back to them when we talk about the cardiovascular system. And beta, there are three of them, three subclasses: beta 1, beta 2, and beta 3. Okay. So make sure that you familiarize yourself with that table, because I promise you they will come back when we address the cardiovascular system. And also, meaning both the heart and the blood vessels. Very interesting topic, by the way. So just, familiarize yourself with those concepts. So those are the functional differences compared to parasympathetic. And we're going to go to the parasympathetic on the next slide. Here you see now in the case of the parasympathetic, we have it's the same neurotransmitter, ACH. So the preganglion neuron releases ACH. The postganglion neuron also releases ACH. Right, so both neurons, in the case of parasympathetic, are cholinergic. In the sympathetic, the preganglionic is cholinergic. The postganglionic is adrenergic. But in the parasympathetic, both pre and post are cholinergic. However, even though it's the same neurotransmitter, the receptor is not the same. The receptor for here is nicotinic cholinergic receptor. This is ionotropic, ion channel, right? This is fast response, ion channel. Whereas for this ACH binds to its receptor, this receptor is not nicotinic, it's muscarinic. And this is a G protein coupled receptor, metabotropic, slow response receptor. It's not an ion channel. So those are functional differences between sympathetic and parasympathetic. So again, one more time, you have structural differences and functional differences between these two autonomic nervous system, between these two visceral motor system of the nervous, motor division of the nervous system. So on that note, I'm going to end today's recording. And then until next time, take care, be safe out there in the meantime, and study well.